In problem 4 of the notes, we're going to talk about how natural logarithms are used with rocket launching. A spacecraft can attain a stable orbit of 300 kilometers above the Earth if it reaches a velocity of 7.7 kilometers per second. So this is just like we need to get to 7.7 in order for it to be safe. The formula of a rocket's maximum velocity in V in kilometers per second is V equals negative 0.0098 t plus c ln r. The booster rocket, which is the rocket that helps it get out there, fires for t seconds, and the velocity of the exhaust is the letter c in kilometers per second. The ratio of the mass of the rocket filled with fuel to its mass without fuel is r. Suppose that the rocket shown in the photo has a mass ratio of 25, it has a firing time of 100, and it has an exhaust velocity as indicated. Over here we have 2.8. Can the spacecraft attain a stable orbit of 300 kilometers above the Earth? So in other words, they're asking, can it reach the velocity they indicated? So what velocity did they indicate? They said it has to reach 7.7 kilometers a second. Now, the mass ratio we use is the letter R, and they're telling us in this problem that the mass ratio is 25. But what does that mean? That means that the rocket filled with fuel is 25 times heavier than if it didn't have any fuel at all. They're telling us also in the picture that the exhaust velocity is 2.8 kilometers per second. And now we just need to plug it into our equation and figure out if we get this 7.7. So V equals negative 0.0098 times t, and in this problem they told us that is going to fire for 100 seconds, plus the little c, which is 2.8, that's the power of the exhaust, times ln of capital R, which in this problem is the mass ratio of 25. All we need to do now is plug it into our calculator and see what we get. Negative 0.0098 times 100 plus 2.8 ln of 25. And we will get 8.03. So this is the velocity that it will reach. The question is that a high enough velocity so that it will be 300 kilometers above Earth safely? The answer is yes. It will be safe because all we needed to get 7.7 or higher for it to be safe. So 8.03 is okay. In the got it, we have the exact same question. We're just changing the booster rocket, we're changing the speed and the time. So in part A, they're asking the same question. Will it be safe? Remember, that's like asking, will it reach our desired 7.7 kilometers a second? So now we have a booster rocket, and its mass ratio is 15. The exhaust of the blast is 2.1, and the firing time has been lowered to 30 seconds. So we're lowering everything. We're making it smaller. It's only 15 times as heavier. The exhaust is not going as fast, and we are lessening the firing time. So again, we just plug it in. Negative 0.0098 times the firing time. This time it's gone from 100 seconds down to 30. Plus the little c, which is the 2.1, that's the speed of the exhaust. ln of capital R, that's the ratio, so 15. And plug all that in. So instead of 100, we need to plug in 30. Instead of 2.8, 2.1. Instead of 25, 15. When you hit enter now, you get 5.4. Now think about it. If it needs to reach 7.7 to be safe, is 5.4 safe? The answer is no. because it needs to be at least 7.7. Part B says, suppose a rocket as designed cannot provide enough velocity to achieve this stable orbit. Kind of like this one. This one did not produce enough to actually achieve the safe orbit. Could alterations be made? Well, we can't alter the size, but we could alter the exhaust time, or excuse me, the exhaust speed. You know, the higher the speed, the faster it's going to go. And we could also alter, we can't alter how far above the Earth it's going to orbit, but we could also alter the firing time. And that would be enough to let that rocket orbit safely.